So today, talk about power series. Chapter 11.8. I did have a question before I started, which is, it hadn't even occurred to me to ask you guys this, but since we're back in the classroom again, is anybody actually interested in me posting the lecture notes that I used to make these things? Does anybody want these? I saw some comment where somebody in Calculus 2 was like, oh my God, somebody get me Hamilton's notes on Calculus 3. So if you're interested in these, I have no problem posting them. Like, I don't know if it's helpful or not, but like they're not proprietary. So you're welcome to have them. Okay, I'll put them up. I make them before every lecture. Normally, I don't have time to post them before lecture, but I can post them afterward. Okay. So yeah. So going forward, check. You can check Canvas for class notes or for lecture notes. And then the last thing I want to remind you guys of is that there's going to be an exam. Exam 1 is next credit, which is February 4th. Okay. And of course, this is required to be taken in person. Okay, so before I start, any questions, anything? Doing okay? Surviving COVID? All right, so the idea that we're going to talk about now, I think, is one of the most powerful and important ideas in calculus. It's used all over science, in physics and engineering and math. And it's the idea of most mathematical functions are terrible to work with, so it would be awesome if we could just replace them with polynomials, because polynomials are awesome. Polynomials are awesome and functions are terrible. So I really don't want to work with functions. I want to work general functions. I want to work with polynomials. Okay. That's the basic motivation. So the first idea that you might have that this is possible is if you think about the geometric series for a second. So the first motivating example is the geometric series. So the thing about the geometric series is we have a formula for adding it up for certain values of R, right? One of the things that we learn when we study geometric series is that if you have something of the form n equals 0 to, say, infinity of R to the n. Notice this is the same, starting at 0 is the same as starting at 1 and putting in n minus 1 right here. This is the same geometric series that you know. 1 plus R squared plus R to the third and so on. What does that add up to? There's no A here, so what does this series add up to? When it adds up, what does the geometric series add up to? One of those basic facts you want to know. Anybody? So when R falls between -1 and 1, this adds up to 1 over 1 minus R. So the geometric series formula is A over 1 minus R, but when A is 1, it just adds up to 1 over 1 minus R, right? This is the most useful thing about geometric series is not just that it converges, but you can tell what it converges to. So if you think about this, not as one series for any particular value of R, but you can think about this as a function that you're plugging values into whenever it converges. So the first idea you might have is, well, if this is true for any value of R between -1 and 1, we could actually make this into a function f of x. So let's make a function f of x, which is 1 plus x squared plus x to the third and so on. I know that because this is a geometric series with ratio x, this adds up to 1 over 1 minus x, and this works for any x. This is like the domain of the function, right? Any x value in here can be plugged into this, and we know it adds to that. What kind of function does that look like? Well, if it cut off right there, it would look like a third degree polynomial, right? It's a polynomial. So in some sense, what we've done is we've written down something that looks like an infinitely long polynomial. It just keeps going. It has infinite degree. The powers of x get higher and higher and higher forever. So you sort of think of this as kind of an infinite polynomial. Boy, oh boy, would it be great if we could do that to other functions besides 1 over 1 minus x. So the next thing you think is, okay, well, is there anything else that it works on? This idea of taking a series and turning it into a function by just plugging different values of x into it, maybe we can do it to other things. Okay, so here's another one. Okay, so another example, this is motivating example 2. I'm choosing this one on purpose because I know what it adds up to. But if you look at this series, you write down the terms of it. 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial and so on. If you add that up by adding term after term after term onto it, you end up with a number that's about equal to 2.71, and that should set off all kinds of alarms if you know what 2.71 equals. What is it? E, right. So you start adding terms because you just want to see, does this add up to anything I recognize? And it turns out to add up to E. So the idea you might have is, okay, maybe I can make a polynomial not with 1 as the coefficient. Maybe I can make a polynomial with these guys as coefficients. So I'm going to try something. I'm just going to, this is a like complete speculation. I built this infinite polynomial and it added up to a function. Does this one? Maybe I can say, okay, well, how about we put 1, and then to make this into a power series, to make it into an infinite polynomial, I'm going to put x to the n. I'm going to attach these x's in here. So I've got a variable to work with. So 1 plus 1 over 1 factorial x, 1 over 2 factorial x to the second, 1 over 3 factorial x to the third, and so on. Maybe that works. I know it works for at least one value, because if I put 1 in for the x's, I get this, which is e. If this was something I said, you know, can this be equal to f of x? If it was, f of 1 would be, well, we're speculating here. It's a value equal to 2.71, which we're speculating is e. If I use this as a function and I put 1 in, that series comes out, which is e. What comes out when I put in 0? Well, that term goes away, and that term goes away, and that term goes away, and everything disappears except for the 1. If you put in -1, then you get a series that looks like this. 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial and so on. It's this series, but with alternating terms. And if you add that together, you get that this is about equal to 0.367, which if you've been around E long enough, you realize is 1 over E. This right here is about equal to 1 over E. That's starting to make me think I know what function that is. If you plotted that, you put in 0 and you get out 1. You put in 1 and you get out something that looks an awful lot like the number E. You put in -1 and you get out the number of 0.367. If this actually defined a function, the function it defines looks like this. Man, that is suspicious. Because I know a function that when I put in 0, I get 1 out. And when I put in 1, I get out E. And when I put in -1, I get 1 over E. So I'm just guessing. I don't have any proof yet. I'm guessing maybe this actually is a function and it's equal to e to the s. So the same idea of constructing an infinite polynomial with special coefficients, thinking about it as a function, this thing looks like it's spitting out numbers that if it was a function would be the same as e to the x. So this is the idea of what power series are and why we care about them. It's a replacement for formulas for a function by something that looks like an infinite polynomial. So what we're going to be looking at is the behavior of infinite polynomials when they converge, and what we're going to be building up to, like how to do calculus with them, because they're not polynomials, they're almost polynomials. Okay? But they're still infinite, so there's some subtleties that we have to deal with. But then the last thing we're going to finish the chapter with is how we can actually prove that e to the x is this power series. This is one of the definitions of e to the x. And for any given function, how you can cough up one of these power series that represents it. Okay, so we're going to start with power series, and we're going to build our way up until we've got a method for turning functions into power series, which are called Taylor polynomials. You've seen them before. Okay. So let's start by writing down what a power series is. So a power series, again, this is not abstract mathematical nonsense. Power series are possibly the most important idea in undergraduate calculus. Nobody works with functions, everybody works with approximations, and approximations come out of power series. So power series is a series of the form sum n equals 0 to infinity of Cn x dn, where the Cn's are coefficients, so they're just fixed numbers, and x is a variable. We're taking the idea of infinite series and turning them into functions that we can plug numbers into. So again, if you write this out, this is C0 plus C1x plus C2x squared plus C3x to the third, and so on. Power series is an infinite polynomial. Okay, now there's a more general way to write this. Oh, I guess I should point out here, this thing could converge or diverge for any value of x you put in. Like, is there a value of x that automatically makes this converge? I can think of one. I don't have to test. What's the easiest possible value of x to plug into this thing? 1. Oh, if you put in 1, you're going to get C1 plus C2 plus C3 plus C4 plus C5, and I don't know what the C's are, so they might converge or they might diverge depending on what the coefficients are. What happens if you put in 0? So yeah, the point here is if you put in x is 1, what comes out is C0 plus C1 plus C2 plus C3 and so on, which may or may not converge depending on what this formula says. Right now, this is back to regular old series, but I don't have a formula for these right now, so I don't know. Maybe it converges, maybe it doesn't. Maybe convergent. I can't tell without the formula for the CN. Somebody else said 0. A bunch of people said 0. If you put in x equals 0, what series falls out? C0. Does that converge? Yeah, just one number, right? One number converges. It's a single number. So this infinite series, this power series, always converges when x is equal to 0 because it adds up to something. So more generally, when we talk about power series, we can use the idea that they always converge for a single number. If I put a 0 in there, and I could say, define a power series centered at A. Centered at is equal to A. Looks like the sum from n equals 0 to infinity of Cn x minus a to the n. The reason that we say it's centered at A, because if I put in x equals A, it's got a whole bunch of zeros all over the place. Right? It'll make more sense why we're talking about using the word centered here once we actually have Taylor series and we know what a radius of convergence is. But the basic idea is that I know this series converges when x is equal to a because it just looks like zeros all over the place, just like that. It's always convergent. Equal to a. It looks like a big sum of zeros and a C naught. So if somebody comes along and gives you a power series, the big question is, when does it actually make sense to plug numbers into it? What values of x make sense to put into a power series? And they're not always in a form that's easily recognizable. So if you look at something like, let's see, say this guy, here's a basic question. For what values of x, this is example 3, for what values of x does this series converge? The first question is, how do you even know it's a power series? Why is that a power series? Not a hard question. What is the clue here that you're looking at a power series instead of a regular one? It's got an x in it, right? It's got an x. It has something that looks like x to the n living inside the terms. So this thing is a power series because it has a variable in it. Now, in a lot of cases, it might be useful to write down what this thing actually represents by putting some numbers into it to see what the formula is doing. So this formula if you put in 0, you get, well, you can't put 0 to this one, I guess. So I should fix the series here. 0 doesn't make any sense to plug in. It's okay to leave, like, have indices that don't start at 0. That's fine. It just means that there's no constant term here. So if you put in 1, you get out x minus 3 over 1. And if you put in 2, you get out x minus 3 squared over 2. If you put in 3, you get x minus 3 to the third over 3. And so on. This is the n equals 1 term, the n equals 2 term, the n equals 3 term, and so on. So the question says, for what values of x does this converge? I don't know. If only I had just spent 2 weeks learning all kinds of ways of testing if series converge or not. So what do you think? What's the best test to use here? Given that there's these x's running around. And I would really like a test that when I'm finished with it, I don't have x minus 3 to the n in it. I want the n out. I just want an x minus 3 all by itself if I could get away with that. So both the root and ratio tests will work here. I'm going to suggest that we do the ratio test because this n on the bottom is not to the nth power. So the ratio test, I think, is a more logical approach, right? So what we're going to do is, and this is generally with power series, the ratio test is what we use. Our main tool for the next part of the class is going to be the ratio test. So we're going to test this series with the ratio test. But we're going to do something slightly different with it than we did when we had a series of numbers. We're interested in answering the question, which x's make it converge? So once I compute this limit, this is going to have x's in it. There's going to be x's that are left over because the limit is with respect to n. So there may be x's left over when we're all done, right? When I actually compute this, there will be x's left in the limit. When does the ratio test say something converges? What does this limit have to do? It has to be less than 1, right? The ratio test says when this limit is less than 1, then the series converges. So I'm going to use this inequality to solve for the x values that make the series converge. I'm going to use the inequality. Use this inequality to find convergent values. Okay. So for this problem, this is what I mean. I'm going to give you 3 different examples of what can happen here. So computing with the ratio test, we get the limit as n goes to infinity of an, and here you just have to be careful. The formula we're using here is an is x minus 3 to the nth over n. So we get x minus 3 to the n plus 1 over n plus 1, because that's an plus 1. And now I'm going to divide by x minus 3 to the n over n. What that's going to get me, I carefully make sure that I take the reciprocal and multiply. So you're doing something right with power series. When you do the computation, the powers of x cancel each other and the n goes away. So you've got n plus 1 copies of x minus 3 on top, and n copies of x minus 3 on the bottom. This limit reduces to the limit as n goes to infinity of x minus 3 times n over n plus 1. Now I'm going to do an algebraic trick here that you don't need to do every time, but there's something I'm trying to emphasize. You notice that this x minus 3 has nothing to do with this limit. Nothing. There's no x's in here. Or sorry, there's no n's in here anymore. So if I want to, this doesn't move as n moves. I can actually take this out front and multiply it. And the reason that you do something like this is because you want to make sure that you don't accidentally plug n into this part. Very common mistake. That didn't move with respect to n, so it's constant, so I just popped out of the limit. What's that limit? 1. So the whole thing at the end of the day, you calculate that limit and you get the absolute value of x minus 3. Okay, what do I do with it? Well, the ratio test says, yeah. What the ratio test says is that this series converges. This series converges when this number right here, which is this part right here, if that limit is less than 1, then the series converges. Well, there's the limit. So the series will converge when that limit is less than 1. So what we're left with is the limit as n goes to infinity of n plus 1 over an is less than 1 when the absolute value of x minus 3 is less than 1. And now we're back in 8th grade, dealing with families of inequalities. I'm going to remind you that this is going to be something we got to do a lot in here. When you have an inequality involving an absolute value, this is really 2 simultaneous inequalities. You drop the inequality, but you have to put 1 and its negative below it. I feel like it's an and situation. The idea is that this absolute value of inequality turns into this. And now we can just do algebra on it. It's an algebraic inequality. I can add 3 to both sides. So what have we done? The point of all this work, the original question was, what values of x make this series converge? And the answer that we came up with is, at least these values do. Any x between 2 and 4, not including x and 4 necessarily, will make that series converge. So if 2 is less than x, which is less than 4, the sum of x minus 3 to the n over n converges. So the ratio test now is not being used as a tool to check convergence. It's being used in the other direction as a tool we're using to find the x's that make something converge instead. Okay. Now, that's not the only possibility. Here's example 4. So let's consider some factorial x to the n. You should already be suspicious because, by the way, what's 0 factorial? 1. By definition, 0 factorial is 1. So 1 plus x plus 2 factorial x squared plus 3 factorial x to the third plus 4 factorial x to the fourth. That doesn't look like any series I've ever seen converge, given that the coefficients here are just running away to infinity about as fast as possible. But we'll test it anyway to see if there's any x we can plug in that makes this work. So again, we're going to find the x's that make this convergent using the ratio test. So we will find convergent values of x with ratio test. Limit goes to infinity and n plus 1 over n. What do we get? N plus 1 factorial over x to the n plus 1 over n factorial x to the n. Which is, if n goes to infinity of, okay, so n plus 1 factorial over n factorial simplifies into an n plus 1. And x to the n plus 1 over x to the n simplifies into an x. Now I've got a piece that doesn't involve n, so I'll pull it out of the limit. Where does that limit go to? Infinity. There's nothing to counter this. N is going to infinity, n plus 1 goes to infinity. Unless what? There's one single value of x that makes that not happen. 0, right? If there was a 0 right here, 0 times anything is 0, right? Unless x is equal to 0. So, are there any values of x that can make this expression right here smaller than 1? There's just that one. The only value of x. The only value of x. With the limit as n goes to infinity of an plus 1 over an less than 1, there's a single value that does that. And that value is x is equal to 0. That's kind of a boring series. It converges for one value. And it's basically just a list of zeros in that case. Okay? So there's the second possibility. The first possibility is a series converges for a band of numbers. Finite band of numbers. The second possibility is the coefficients grow so quickly, only the center of the series will make it converge because you're just adding a bunch of zeros. Now let's look at an example that spits out the third possibility. Well, how about the series we started with? One of our motivating examples was this guy. Now we don't have coefficients that are running away to infinity really quickly. We have coefficients that are going to 0 really quickly. So what values of x make this converge? by the ratio test. And I can keep this limit. X to the n plus 1, n plus 1 factorial. Let me know if I make any mistakes when I'm doing these steps. I believe this just turns into this. I get an x over n plus 1. X to the n plus 1 over x to the n cancels into a single x. N factorial over n plus 1 factorial is behind an n plus 1 and everything cancels. What's that limit? 0. Always. Absolute x times the limit as n goes to infinity of 1 over n plus 1. Remember, x is constant, right? X is just some number. I've got this thing is going to 0, so the whole thing is 0. No matter what choice of x we make, that limit is 0. For any choice of x. That means for any choice of x, the limit as n goes to infinity of an plus 1 over an is less than 1. 0 is less than 1. So that series converges for every value of x. No matter what x you put into that series, it converges. If you want to think about this from an orders of growth standpoint, it's because you're dominating an exponential function with a factorial. No matter what x you pick, the factorial is going to win. So this converges for all. The fancy math way to write this is for all x in the real numbers, which is fancy r. Or you could write minus infinity less than x less than infinity. Or you could write x in the interval from minus infinity to infinity. There's a lot of ways to write this down. Pick your flavors. You just write for all real numbers that you want. The point is, this series always converges. That actually should give you more evidence that this might actually be equal to e to the x, because e to the x is a function that's defined everywhere. So the theorem at the end of this is what we've done here. This is all that can happen. This is the only possibilities that can happen with power series. They converge only at one number. They converge for every number, or they converge for some sort of interval. This is the theorem. I'll write down some examples. So the theorem says is that for any, don't worry, there's no proof coming here. If you're interested in the proof, you can read it. For any power series of the form Cn x minus a to the n, one of three things can happen. One of three Cn x minus a to the n converges only when x is equal to a. That's the series of zeros. The example that we saw of that was this one with the stupid coefficients. N factorial x to the n. Coefficients grow really quickly, the x's can't counter it. This can't converge unless it turns into 0. Second possibility. The sum of the coefficients of a series converges for all x. That was this possibility. Here the coefficients are going to 0 so fast, no matter what you choose for x, the coefficients win. The third possibility, there exists a positive number r, which is usually called the radius of convergence. So that the series, the series converges for x minus a less than r. That was like the inequality we solved. And diverges for values of x that are further than r units away from a. And that was the series. X minus 3 to the n over n. Remember, that only converged for values of x between 2 and 4. And in this problem, the radius that we found when we computed that limit was 1. So another way of interpreting radius of convergence is this converged for values between 2 and 4. The center of the series was at 3. The distance from the center to the edge of convergence was 1 unit. So if you think about this on a number line, if you have a 3 right here, which is the center of the series, we know that we can go up to 4 and everything is okay. And we know we can go down to 2 and everything is okay. So that right there is why we call it the radius of convergence. It tells us how far from the center we can get and still be okay. For those of you that are interested in why we would use radius to talk about a length like this, I'm going to do a brief divergence here for like 5 seconds to tell you secretly all of this is in complex variables. And in the complex plane with complex inputs, there's a circle here with the same center, and the radius is actually the radius of the circle. So the natural place to consider power series once you get higher up in your engineering and science and math work is actually as functions of complex numbers. I'm not trying to scare you with complex numbers, but they are lurking out there. So I got a question, which is what happens at the edge? And so what we've got right now is I have this series, f of x, and so this series that look like x minus 3 to the n over n. And we figured out that it converged for 2 less than x less than 4. What about 2 and 4? I mean, I know it converges between 2 and 4. The next question is, what happens at the edge? Can I use 2? I mean, it converges as I get closer and closer and closer to 2. Everything's cool. As I get closer and closer to 4, everything is cool. So the next question is, what about x equals 2, x equals 4? How do I test those? I mean, remember, the ratio test can't tell me anything when that value was equal to 1, right? When the ratio test spit out of 1, it can't tell you any information. And the way this works is if you're at the edge of the interval, the ratio test is spitting out a 1. So it tells you what happens in here, but it can't tell you about the 2 and the 4. So what do? Plug them in. If we plug in x equals 2 into the series, what do we get out of this? We get 2 minus 3 to the n over n, which is minus 1 to the n over n. Converge or diverge? Five. Yes, this converges by the alternating series test. I mean, those are the 1 over n's are tending to 0 in a decreasing way, and the series alternates. So this is a convergent series. So 2 is good. 2 works. About 4. You put in x equals 4, you get out 4 minus 3 to the n. Is the sum of 1 over n. Why not? P series. This is divergent. P equals 1. The harmonic series. It's divergent. So if I want to give you the actual answer about when this series converges, the ratio test tells you something like this, where it's telling you the inside of the interval of convergence. You have to check the outside points. It's your job. So in this case, here's the scenario you're looking at the end when we put all this information together. So the series here was this. Here's the number 3, which was the center. We already know that we're okay up to 4 and down to 2 as long as I don't touch 2 and 4. This distance right here is the radius of convergence. The fact that we check the endpoints means I can fill in. So basically we have this information if we're going to use this kind of notation from back in pre-calculus. That's where we know it converges right now. Now we're going to add the endpoint information. Can I fill in any of those dots? And the answer is yes, I can fill in 2 because it converged there. But I can't fill in the 4 because it doesn't. X equals 2 converges. X equals 4 diverges. And so the domain of the power series, if we're thinking about it as a function, or usually what we call it in this context is the interval of convergence, is including 2, not including 4. All of this information is required to use a power series. It's not enough just to have a formula. I have to know when that formula is legal to use. So when these things come up in science, when they come up in science classes or science projects, theories of science, theories of math, theories of engineering, it's not enough to know something can be expressed as a power series. You actually have to know when it's a valid object to be working with. It's one of the biggest pains about working with these things is having to carry domain information around. Okay. All right, so let's find, I got one more example of you here. Today. So let's look at this one. So how would this kind of question be asked of you? So I'm on example 6. 5. 6. Okay, so here's example 6. The normal way this question is asked is something like, find the interval of convergence of n equals 0 to infinity, 0 this time, yeah, of -3 to the n x to the n over the square root of n plus 1. We're going to approach this like we approached the last one. The order is going to be, we're going to do the ratio test. This will give us the radius and the inside interval. And then we'll have to test the endpoints. Okay, 2-step process. And we're trying to figure out where a power series converges. Again, in almost every context, because of the x to the n running around, and the way the coefficients are set up, we're going to be using ratio test. Ratio test gets us what? -3 to the n plus 1 x to the n plus 1 over the square root of n plus 2. If I put n plus 1 in for n here, n plus 1 is n plus 2. Times root n plus 1 over minus 3 to the n. To the n. an plus 1 divided by an. Algebraically simplifying that gives us, okay, so the minus 3 is left on top. And then there's an x that's up there, and this x. And now I've got this root n plus 1 and root n plus 2 that are left over. The minus 3x has nothing to do with the limit. And that limit is 1. You can use L'Hopital's if you want. You can use algebra if you want. If you don't see it right away, do it that way. I might circle lead terms and say, okay, it's like root n over root n. When n gets big, this limit is 1. So the whole thing turns into that. What do I do with that information? Set it less than 1, right? That was the left-hand side of the inequality. So this thing is going to converge whenever this is true, which is the same as saying that this is true, which is the same as saying this is true. Make sense? So this is the interior of the interval of convergence. By the way, what is the radius of convergence here? It's 1/3, right? The center was 0. I go up 1/3 and down 1/3. The radius here, r, is 1/3. From the center to the edge was 1/3 units. Now what? I got to test the endpoints. Where do I get the endpoints? Right here. I need to test and see if these strict inequalities are actually less than or equal to. So you plug those in. If you plug in x is equal to 1/3, what comes out of the series when you put 1/3 in there? So it's the sum of minus 1 to the n plus 1 to the n times 3 to the n times another. I'm trying to plug that into this. Maybe I'll do it over here. X equal to 1/3 goes in here and turns into the sum from n equals 0 to infinity of minus 1 to the n over the square root of n. Convergent or divergent? Why is it convergent? Alternating series test. The limit of 1 over root n is 0. It's a decreasing function. This converges by the alternating series test. Basically, putting the 1/3 in here didn't cancel the negative in this term. Right? Negative 3 to the n is the same as minus 1 to the n times 3 to the n. What if you put in x is equal to minus 1/3? Well, then you get out the sum from n equals 0 to infinity of minus 3 to the n times 1 minus 1/3 to the n. You just get out 1 over root n. Convergent or divergent? Why? T series of p equals 2, or not. T series of p is 1/2. This is divergent. So the question was originally, what is the interval of convergence? And the answer is, well, there was 0. I had a circle at 1/3. I had a circle at minus 1/3. My interval was between those. The radius is 1/3 because the distance from here to here is 1/3. Which dot can I fill in, if any? Well, 1/3 is good and negative 1/3 isn't. So the interval of convergence runs from minus 1/3, but not including it, up to 1/3 and including it. It's a typical structure of these kind of exercises. Okay, so the basic approach and tool set here is what we've just done. You test convergence with the ratio test, and you test the endpoints using what we already know about T series and alternating series. Where this goes next is how we do calculus on these things. So it would be really nice to know, for example, I know how to integrate a polynomial. Can I integrate that? Is the question. Is it legal for me to think about that as a giant polynomial and integrate it or take its derivative? Is that a valid thing to do? Fortunately, the answer is yes. It turns out you can use calculus on these things, but only when they converge absolutely. So oftentimes it's the case. I mean, that's why we use the ratio test, is we want absolute convergence. When we have absolute convergence, calculus works. Okay. So we're going to do calculus with these next. Once to use these series to get new ones. Once we've got calculus, then we'll do a method for generating these things from existing functions. All right. So I'll have this homework posted tonight. Thanks for your attention. I see you guys tomorrow. Oh yeah. Oh no, I'm shattered.
You have to prove like alternating series tests for endpoints, like you have to prove like
I would actually say at this point, like in this section, you can just assert that that converges by the. It'll be obvious if it doesn't. Yeah, so you can do that, but then you need to like discretize it. Right? So you don't have a continuous function in your but that's actually kind of the idea behind integration is that yes, if you know this converges absolutely, then you can basically sum over some partition. And then these things like you're absolutely right. That's like this is the core idea of why integration works. Okay. We're not going to do the Riemann sum. Really yeah, no. That looks like a lot of work, but I don't want to do it. Yeah, no. So that's the sort of thing where I'm just going to say that it's legal to do calculus on it, and we're going to work with the calculus. If you actually want to see the proof of it working, you can just go do that. Like that's Stuart does it in exquisite detail. Okay. Bye.
Is today going to be your office hours or what afternoon?
I have a stupid. I'm gonna try to do it tomorrow. Actually, like in the afternoon. I couldn't do it today because we have hiring days. So,
when you feel like an email or something?
I just haven't had a chance to sit down and do it. Absolutely, and I'm also looking for